afternoon, everyone. So today we are going to jump into the derivation of the Fokker-Planck equation, right, which is basically going to tell us how the conditional probability distribution is going to evolve. All right. So if you like, this will be a formalized version of the derivation that we saw from Einstein's paper. So the starting point is where we left off in the last class, right, where we introduced the idea of general stochastic processes and saw that we needed not just the probability distribution of finding a particle at any time, at any point in space, but rather we needed to know the probability density of all possible trajectories, right, in general. But then we saw that if we restrict ourselves to what are called Markov processes, right, where what's going to happen next only depends on the current state, then you can build up these trajectories by taking the individual steps, right. So you can write a probability of going from A to B to C as a probability of A to B and then B to C, right. So this is the Markov chain, and in the simplest case, A to B, B to C will not depend on A, B or C, but maybe the distance between them or some other property, right. So that's how one builds complicated trajectories with relatively little information, right, with these assumptions. So we're going to assume that we're looking at Markov processes, and that too continuous Markov processes. Remember, we ended the class with the Lindbergh condition, which basically is a way of saying that the rate of taking big jumps is 0. Okay, so we are going to use that assumption and also bring in a formal way the assumptions Einstein made regarding the first and second moments of the steps, right, which he took for Brownian motion. So those steps are nothing but transition probability, right, conditional probability densities when the time gap is small. So that's what we're going to start with and then see how we can do the derivation. The point is we want to get the Fokker-Planck equation. And we're going to make some assumptions now, so let me list them down. Okay, so the first is to say that the probability of taking big jumps, okay, is going to be 0. Okay, so the idea is we're going to, as usual when we try to talk about continuous processes, introduce the idea of some epsilon, which can be made, which is positive and can be made as small as we like. So something greater than epsilon conveys the idea of big jump. Okay. So now for any epsilon greater than 0, what we would like is that the following probability this is the first thing I want. So if you look back to your Lindbergh condition, it required that the integral of so the Lindbergh condition looked at the integral of this probability and said that the integral for x minus z, where the step is greater than epsilon, that integral should go to 0. Okay. So here we are assuming something which will guarantee that, which is that the PDF itself shrinks, right. So this PDF should shrink faster than delta t, okay, so that the rate, if you like, of these jumps is 0. So this is for all big steps, right, greater than epsilon. So this will guarantee that the process is continuous, that I'm not going to have these big jumps. And now we'll bring in the assumptions that basically say that whatever stochastic process I have, right, which is described entirely by these jumps, right, because remember it's Markov, so if we know the probability density for any jump, small jump, I can build up, you know, the chain. So I want to say something about these transition probabilities, and particularly I want to say something about the first moment and the second moment, which, if you recall Einstein's derivation, will be related ultimately to the velocity and the diffusion. Okay. So now that we know that big steps are not okay, right, so as I forgot to say this. So it is this in the limit of course that delta t goes to 0. So of course some big delta t this doesn't make sense, right? But if you shrink delta t to 0, then you don't want to have big steps. So you choose any epsilon as some cutoff that which is also small, like epsilon is also small, and you're saying that I can shrink delta sufficiently so that probability of stepping beyond the epsilon is 0. Okay. So everything is going to be in the limit of shrinking delta t, okay, because ultimately that will be used to get a differential equation for p. Okay, so that's the first point. Now second point is what happens within this epsilon. Right, so now I choose an epsilon, big steps are not allowed, but the small steps within my epsilon, that should have a first moment and a second moment. Okay. So again, we'll take the limit. And this time we are going to do the integral less than epsilon. Okay, so we are looking at small steps, and our statement is going to be that the step multiplied by the PDF, given that I am starting from z at time t. Okay, so I am at z at time t, the probability to take a step to x, where that step is going to be small. Okay, the first moment of that, I want to be integrate over all x, okay, wherever I go. So this I am going to say is you have a finite first moment. That first moment is of course going to be a function of where I start from. Okay. Even mathematically you see I am integrating over x, right, so x will not survive. And then there will be some small epsilon order correction. So as I make epsilon smaller, those terms can be dropped. Okay, but this term will survive. So if you like, this is A is basically like a velocity. So I am defining the velocity, right, of this continuous process. Okay, so as I shrink time to 0 so that it starts looking like a continuous process, I am saying that I am going to have a mean step. Okay, this is nothing but the mean step, right, which has a velocity a. And this a, if I take any finite epsilon, the a will get corrected, but as epsilon, so delta t is anyway going to 0, and I look at smaller and smaller steps, then I am really going to get a motion which has a velocity. Okay, so that's why this 1 by dt is what makes it like a velocity. So I am taking a mean step in intervals of time delta t which has this a. Okay, any questions? So this is what Einstein also assumed, right? So if you think of x minus z as delta, and this distribution of taking the step delta is like what we said, phi of delta. So you said integral delta phi of delta was something, the velocity. Right? But what we have done here is we are being more careful, right? Because we have defined the fact that I am only going to do this integral for small steps. Right? That's what we had not said last time, right? We said nothing about how phi decays and so on. We just assumed that it's okay, and we did Taylor series and whatnot. Right? So this assumption is going to be important for us later to be able to do a Taylor series development properly. And you can ask me what will happen outside epsilon. Well, that I already know that this guy is going to go off to 0. Right? So I don't have to worry about the stuff outside epsilon because of this assumption. And here we are only going to consider such processes where stuff outside epsilon can be dropped. So there are no big jumps. Now there are of course situations where you can have big jumps. We won't do it in this course, but Gardner's book treats that extension. So what I'm doing today is only for processes which don't have discontinuous jumps. But we can revisit that later. Okay, so now similarly I'll have a condition for the second moment, right, which is going to be similar to what Einstein assumed again. So today we'll only do one dimension, right? That's why you see I'm only working in x. But what I'm doing here can be extended to n dimensions. So this could become a vector, right? Then I would have x minus z vector and so on. Right? So again, those developments are straightforward once we do the 1D case, and it's available in Gardner. So let's just focus on 1D today. Okay, again we are going to look at small steps. Okay, x minus z square. And the same story. and now I'm going to call this B. Okay. So you see, this is like the second moment. And you can already see that B has a character of diffusion, because what you're saying is, I have a mean value for the delta step squared per unit time. Right? But what is the step square per unit time? That is the diffusion. If I was observing a phenomena, a Brownian motion, and I measured the distance square that it covers in a unit in some amount of time, right, then I know that the ratio of that root mean square distance, right, divided by the time is the diffusion coefficient. Just like I know that the ratio of the displacement by time is the velocity. Okay, so it's like a definition of these two things here. Now, of course, it remains for us to show, fine, if I have some process and I can measure these quantities, how does that help me understand how the property distribution evolves over time? Right, these are just for small steps, delta t. So maybe the idea is I could have some arbitrary complex process. It need not be Brownian motion. It can be whatever stochastic process, smooth one you can think about. But the point that I'm making here is, if you stop at some time and just look at small intervals of time, then you can always get some local velocity and some local diffusion coefficient. But note that I'm allowing it to be a function of where I am. Okay, so when we think of normal Brownian motion and diffusion, these are constant. Okay, especially diffusion, then you will get your nice intuitive idea of diffusion. Okay. But suppose your diffusion coefficient is a function of space, then many complicated things can happen, right? So you can start somewhere, and instead of some group of particles spreading uniformly, they could spread in some weird way, because maybe the diffusion in some location is close to zero, some is very fast, it will have some weird kind of spreading behavior. So you can imagine particles spreading like a star because you have pattern diffusion in space, just as an example. So arbitrarily complicated things can happen with this, right? This does not mean that I'm starting and saying, okay, I'm only looking at processes which have a velocity and a diffusion, so I'll always get some advection diffusion. That's not what I'm doing, right? Because they are only local statements. Right? So it's like saying you look at some arbitrary complicated motion. If you think about an ordinary differential equation, right? You have some arbitrary complicated motion. At any point in time, if I take a small step, I can define a velocity. That you can always do. The complexity will arise if that velocity now depends on the position of the particle in phase space. Then you can get any kind of complex dynamical system. Right? It's not that the velocity is constant. This idea you have to keep in mind. So it would be like saying, okay, any ODE will only give me constant motion. That's not true. It is just that I can define a velocity locally at any point in time and space. Right? But if that velocity is a function of time and space, I'll get super complicated motion. So it's the same idea. So this is completely general, that you can apply it to any continuous stochastic process. Right? But you can always define this locally, right, for the delta t. Right? Now the question is, I want to know how this probability will evolve if I start at some z and then go forward to some x as time grows. Right? That will tell me if I start all my particles at z and then if I go forward in time where delta t is not small, right, what will happen to the distribution? That's what I really want to know. And that doesn't have to just be advection diffusion, because it will be somehow a compounding of these things, which can be very complicated. Okay, so this is important to keep in mind. So if you want to relate it again to ODEs, it's like saying, I'm simply saying that at any point dx by dt is some velocity, but that can be a function of x and time. That's all. And we're going to use this to get a PDE for P. In the ODE case, it is immediately obvious. If I say dx dt is equal to v, you just integrate that. That is the equation. But here saying this doesn't give me an equation that I can evolve. Right? That's where I need to do some mathematical work that we are doing today. Okay, but this is the equivalent of stating that in the ODE problem. Okay, so I've given the two moments. Now you should ask me, okay, why should I stop here? I can always define maybe a third moment. Okay, so now we are going to see that the third moment and higher moments will necessarily vanish. Okay, so let's see that. And also what our demonstration will show, why we cannot assume that this is going to vanish. Right, so this was again a missing point in our first class, right? We didn't really address what is happening to the higher moments. Okay, so let's consider the third moment, what it would look like. Right? So I would again have limit Okay, so this would be our third moment. It is our third moment. Now, why am I saying that this will vanish? Let's see what we can do. Okay, we can say that I have this and I know that this must be, so I will suppress the 1 by delta t business. Let's just look at this part. Okay. So, this thing must be less than equal to if I put mod on this. Okay, because this can have positive or negative values. But if I take only the mod of x minus z, then of course that will have to be greater than this integral. And what I want to do is show you that this integral goes to 0. So I show you that something greater than it is going to 0, then you can be sure it's going to 0. This is the usual way of showing inequality. So I can say this is less than x minus z square mod x minus z, right, times the probability, same thing. Okay, I'm not writing that, but same thing. Okay. Thanks. You carry the limit everywhere. Okay, now what I can do again is to note that this x minus z, of course I forgot to do this, x minus z, we're only looking less than epsilon. The same story. Okay, so now you can see this part is the second moment. Right, exactly. Only problem is this fellow. So can I pull him out somehow within the inequality framework? Right, I just replace it by epsilon, right? That's the upper bound of this magnitude, right? Because of my condition on the integral. So this in turn must be even smaller than epsilon, right? Epsilon times. So I'll pull out the epsilon here, right? And this 1 by delta t, etc. in the limit is just going to give me b. Right? And higher order terms. So you can see that the third moment will already be like epsilon, right? There is no non-epsilon term in the third moment. And so it can be dropped. And you can do this for any other higher moments also. It will just get higher powers of epsilon. Now why couldn't I do this here and get rid of the second moment? Right, I would have x minus z square. Can I do the same thing and show that b will also be epsilon times a, or no? So that will tell you why we had to keep the second moment. So you look at the derivation, right? This is fine. What let me do this is that x minus z square exists. If this is also x minus z, right, then I cannot pull it out. Okay. So because it's square, it's already positive, and then I can use it exactly without putting the bound on it. So this idea only works for higher derivatives because this I can keep as is without doing anything. So I only put the mod on this part. Because the other thing is positive. If I had x minus z and put mod on x minus z, that doesn't make sense. That thing will not be less than taking x minus z square because that is positive. You see, x minus z square is positive in this definition. And if I split it into x minus z, put mod on 1, the other thing has a sign. Right? So that will actually be smaller. It will not be an upper bound. Here, putting the mod makes it an upper bound because this is positive and this is negative. Right? If you try to do for second moment, you will flip the situation. This would become negative and that would be always positive. Okay, so you can only do this for higher moments. So that basically it's like saying what we already know, right? So if I have a mean, fine. Second moment can always contribute in a non-trivial way because you are squaring it. It's like saying displacement is velocity, root mean square gives me diffusion, and root mean square can be larger than the velocity. Velocity could be 0, right? The mean step can be 0. This will be non-zero. That's the whole point of diffusion, right? But the third moment will be smaller than the second moment. So it's a mathematical thing, but it's also reflecting what we intuitively feel, right? That I can go forward, backward, and have 0 displacement, and yet have a root mean square positive displacement, right? So this and these are independent. But then once B, anything after that can be related to B. Okay, again, I have had to use this fact that I can only look at the integral for small steps. If that's not true, then this doesn't work. So if you're thinking of some process where large steps are possible and so on, then the higher moments don't have to be smaller. Okay, so everything is connected to the fact that we are only looking at small steps because we have such a process where high steps are going to 0. Okay, so this is very nice because it tells us that any higher order step, we don't have to think about the higher order moments. Okay, they will all be small. So when epsilon is made 0, taken to 0, all those terms will drop out. I'll only be left with a velocity and some kind of diffusion coefficient. And these are basically the definitions, if you like, of this velocity and diffusion coefficient if I'm monitoring a process in a small time interval. Now the question is, how can I use this information, this definition of velocity and diffusion kind of behavior, to get an evolution equation for the probability distribution itself? Okay, that's what we're going to do now. Okay, so everything I've done here is 1D, right? For the n-dimensional version, you can see Gardner's book. I think it's chapter 4, page 47. So it's a natural extension of this, but because you work in vectors, and you'll have to use Einstein notation, and there's some nuances, but the same logic follows. Yes.
Does that mean the sum of absolute increment goes up to infinity?
Does what mean?
Sum of absolute increment. So in the first moment, you wrote in x minus z bracket, right?
Yes.
If I replace it with x minus z mod, so that will go to infinity, right?
No, that will be of order epsilon. Why will it go to infinity? I'm only doing the integral for small epsilon. Okay. Any other questions? So the one way to think of this is, I'm basically saying this probability rate is 0 outside x minus epsilon. Within it, it is not 0. It has a mean and a diffusion coefficient. So at max, this can be uniform, right? It can be 1 everywhere and go to 0. If it is 1, then you will just get epsilon. But then in general, it will be a smooth decay, so it will be something less than that epsilon. But then I'm dividing it by delta t, right? So that gives me the velocity. Okay, so let's move on. Okay, then as we see how these things are used, you can think more about it. Okay, so now we want to get an evolution equation for E of so I want to find an evolution equation ultimately for this conditional probability, which is basically saying I'm starting at some position y at some original time t prime, and then I wait for arbitrarily long time so that t prime becomes t. And what is my probability of finding this particle at some other position x? So here x and y are not close, t and t prime are not close. And if I have this information, then I have everything about the process, because I can apply this anywhere, right? I can take any point and see what is this probability distribution as I go forward in time. I can do it in small steps, big steps, however I like. And my hope is that, or my anticipation is that because I'm looking at a Markov process, this process itself can be, so let's say I choose some value, right, t prime y, and I choose some x and t. This path can be built up out of infinitesimal steps. Okay, so I can construct this by doing a chain of small steps, right, and using the Chapman-Kolmogorov equation. That's what we derived at the end of the last lecture, right? So basically says I can go from y t prime to x and 3 to some intermediate step, provided I integrate over all those intermediate steps. And you can imagine I do this in small steps. And if I do it in small steps, I should be able to use my information about the velocity and the diffusion coefficient to figure out what those small steps are and kind of pile them on, right? But instead of doing it in this arbitrary way where I choose some small step, that would be like a numerical method. But if I can formalize this, I should be able to derive a differential equation directly for P, after which I don't have to worry about probability anymore, in the sense that I will get an equation, deterministic equation for the P. Then I can solve it the way I solve normal PDEs. Okay. So in some sense, this approach escapes the probability universe, right? I start with these ideas, I use it to define A and B, but if I can derive a standard deterministic evolution equation for P, then I can use all my mathematical tools that I use for transport equations, right? I can forget about the fact that things are stochastic now in some sense, because I'm just solving a deterministic equation. And then, so this is like approach 1, right? Then later on in the course, we will see how we always stick with the stochastic process because we follow the trajectories. But right now we are doing this, right? So we're not, the idea of trajectory is there, right? But one can also see that if I just do this formally in a mathematical way, I don't even have to think about the trajectory, right? I can directly come here and get the equation. So this is the first way of approaching it. Okay, so we want to get an evolution equation for P. In other words, I want an equation for ddt of P. So how do we do this? One possibility is I just say, okay, I want to find time derivative of P, and I try to use the definition of the time derivative, which is P at t plus delta t minus the same quantity at t, and then try to do something. Okay. Now it turns out that you cannot go anywhere with that approach. We'll see a bit later why it doesn't work. So what does work is to think about how an expectation of some function will evolve. So let's say I have this process again which describes how x is changing, okay, how the position is changing. And now I define some deterministic function f of x. Okay, I think of some function f of x, some arbitrary function. It can be just x or x square or whatever, and I want to find how the mean of that will evolve. So the mean of this could be sine x, right? So I just specify some function. But because x itself is fluctuating, this quantity will fluctuate, and I want to know its mean. The benefit of doing this is it immediately casts this under the integral, and then we can use certain mathematical steps to bring in our integrals on the top, because the b and a are defined in terms of these integrals. So what I want to do is look for this partial derivative. Okay. So this is how I would define the ensemble average of f, is to multiply it with the probability distribution, right, and integrate over x. Okay, so the conditional thing just says, okay, how will the mean of f evolve, provided I start at y comma t prime, that's it. Okay, so at y comma t prime, this will just be f of y, right, but f of y will then evolve in different ways as x evolves, but there will be some mean of all those trajectories, that is this quantity. Okay, now I want to see how the mean is evolving. Now the important thing is I have not specified f, and that's going to be very important, because it's only when f is unspecified that looking at the evolution of this integral will allow me actually to access the evolution of p itself in principle. So even before, without going into the mathematical details, you can ask, how can I expect from looking at this quantity to get any information on the evolution of p itself? because it would seem like I'm averaging out the p. Right? I'm only going to get some part of the information. But that is not true because I have not specified f. So suppose f is a Dirac delta. Right? Suppose I could get an equation for the evolution of this for any f. Right? So the derivation we're about to do, let's say I'm able to get the evolution of mean of f of x for any f. Then I can choose the f, right? And then I can choose f to be a Dirac delta at different locations, and from that I can construct how the whole p function is evolving. Because if f is a Dirac delta at some position, x equal to x prime, then I'll get the value of how p is evolving at x prime. Then I can shift this x prime and I'll get the whole function. Right? Or another way to think about it is this will tell me the evolution of p projected on different f's. And now if I choose f's to be a basis set in the space, I'll be able to reconstruct the function. So let's say I'm in a periodic domain. If f is a sine series, it would be like taking the Fourier transform of p and getting the evolution of all the Fourier modes. Okay, that's another way to think about it. Or if you don't like thinking about basis sets, you just think about f being a Dirac delta which I can shift. So that's just to say in principle that when we write this, we are not compromising ourselves and saying, okay, I'm going to, even if I find this, there is no way I can get information about p. Right? This is not true because I have not specified f. Right? And this sort of idea is the basis of things like weak formulations of PDEs and ODEs, or things like the finite element method, the Galeckin method, right? Which solves some equation by looking at projections of it, and provided you can project it on any function of your choice, you can reconstruct the information. Okay. So let's keep that in mind, and we will use that at the end to specify f in some way to get an equation for p. Okay. But that will involve some mathematical steps. What I don't want you to think is it was like some magic, right? Because right in the beginning, you should have this idea in mind that just because I'm looking at this doesn't mean I've lost information. I can always get it back because I can choose f. Right now, if I fix f to say, let's say f is only x, then what will I get? Only the mean of x. Right? Suppose if I put f of x equal to x, that's the first moment. I'll only find out the first moment is evolving of x itself. If I put x square, I'll get the second moment. So that is limited information. But if I leave f arbitrary, then I can reconstruct the p. Talking about moments, I could choose f to be 1, which will just give me 1, x, which will give me first moment, x square, x cube, and I can keep doing this. Right? And you should know that if I have a PDF, if you give me all its moments, infinite moments, I can reconstruct the PDF. Right? That also is possible. So in many different ways, you can see that the fact that f is unspecified is giving me the possibility of getting back information on p. Okay. Now, how we will do it, we are going to see. Okay, very good. So this now, because I can pull this in, I want you to see that this is basically the same as saying you just remember that, we'll use it later. Let me call this equation 1. Okay, but we are going to work with the LHS right now, but the RHS we'll keep in mind. So what I want to do ultimately is I want to bring this into some form where I have f into some stuff equal to this, then I can get dp dt is equal to that. That's what we'll do later. Okay, now what can I do with this? I will now use the definition of the derivative on the left hand side. Okay. So because of this, I take the limit okay. Yeah, sorry. So of course, y and t prime are fixed. I'm only taking the derivative on this argument t. T prime is the original time, that's some fixed arbitrary time. Okay, so I've introduced a difference, which is a good thing. And you can see that now because I want to get a PDE, I will want to introduce somehow a Taylor series development, right, which involves a difference of p's. But the problem is that if I have to do Taylor series in space, I need to find a point close to x. And y is of course not close to x. Right, because y is at some old time t prime. And the small time step I am taking, which the basis of hoping to do Taylor series in space is because I am taking a small delta t. But the small delta t is involved here, right, not on the t prime. So what I can do now is introduce an intermediate step. This is where Chapman-Kolmogorov will come, right, and say that, okay, I went from y at t prime to some z at t, okay, and that z at t will be close to x at t plus delta t. All right, so I'm going to take this guy and go from, so here there's nothing for me to do, right, but here I'm going from t prime to t plus delta t, and I can do it through t. So I'll go from t prime to t, and then t to t plus delta t. And at the t and t plus delta t, I should be close by in space. Okay, and then I can use those ideas. So because there I used x minus z, I'll choose the intermediate position to be z, right? So let's see what happens. So I'll call this, so let's say this is term 1, this is term 2. So what happens to 1? So the 1 by delta t, limit delta t and so on is there, right? Let's just look at the integral. I'm now going to introduce another point z and do the integral over the whole z, basically do Chapman-Kolmogorov. And I'm going to come to this position through a z at time t. Okay. And okay, so what I did, instead of going from y t prime to x at t plus delta t, I'm saying I'm going from y and t prime through an intermediate point z at t, okay, and then going from z at t to x and t plus delta t. And this x and z will be close, okay, because it's happening at t and delta t. Okay, whereas y and z are not close and y and x are not close. Okay. And so I can say x minus z is like epsilon, okay, or is small, less than epsilon, sorry. I can make this statement that there is some epsilon such that this x minus z will be small, right? Precisely in what sense? In the sense that I defined there. Right? So already you can see that I have this step distribution, right? So that will be useful for me. Okay, so the first thing is x minus z can be taken to be small, and because this is nothing but the transition distribution, right? So I have introduced that, what I had over there. Right? Whereas I didn't start with it, you see. I started with taking big step, so my information there is not useful because that is for a small transition probability. But by introducing the z, I am now and using Chapman-Kolmogorov. So here I used Chapman-Kolmogorov, right? Right here. to bring in this. So because of that, I now have this transition probability. And I know the property, I mean, I have specified some assumptions on that, right? The first is that if the step x minus z is large, then that thing is 0. So because of that, I can immediately put the integral on z, right, x minus z. So even though I started with the full integral, right, over all the x, over all x, so it's really on the x, right? So over all x, now I know that I can restrict attention only to x close to the z, because otherwise this thing is 0. Remember, I have a 1 by delta t, okay, everywhere. So I did two things. I used Chapman-Kolmogorov and I used the fact that assumption 1 right, and I used assumption 1 to restrict the integral, because I know outside that there is no transition probability. Okay, good. So now I have converted my integral into something that is restricted to x being close to z. Okay, and because of that, now this f of x can be Taylor series expanded. Okay, so I am not expanding the p, okay, rather I am expanding this function which I had chosen to take the expectation of. And so here clearly you can see that I'll have to assume that its first and second derivatives exist when I do the Taylor series. That's fine, I can choose the f to be of that kind. But the Taylor series is possible now. Why am I expanding about z? Because that's how I'll introduce the higher derivatives. Okay. Let's see that. But it's possible to do a Taylor series only when I can say the x is close to z. Then I can expand that f of x about z. In the beginning, I could not do this. And this is possible because of my first assumption, because then I can restrict the integral. So I'm not, the stuff outside epsilon where x is far from z doesn't contribute. Okay. Okay, so what will I get? So f is only a function of x, right? So I don't need a partial derivative. So what I am doing here is Taylor expanding f of x about z, right? So the x dependence is sitting in the coefficients. These things are only functions of z. Okay, so this is at x equal to z. Same here. And then this is the third order term. I'm retaining it just to show that this will drop out. Okay, and we'll see in a moment that these terms will drop out because we have shown already that the third order moments are small. Okay, so I'm just keeping it so that we'll see that this and higher terms are going to drop. So this is x minus something the whole cube. Of course, by 3 I absorbed it into q. Q is some function, okay, which will survive as x minus z goes to 0. Okay, some bounded function. And of course, there are high order terms, but as we'll see, the way this drops out, all the others will also drop out. Okay, so what I can do now is substitute this on top. okay, and then we'll see what we get. You see, so I split it in a way that will be easier to digest. Okay. So when I'm thinking about these terms, okay, I'm going to multiply these guys with this, and I have the x. Of course, everything is under the same thing. I've just written it in this way. Let me put this here. Otherwise, it doesn't matter. It's the same. Yeah, let me put it here. Yeah, fine. But I wanted to think of, when you see x minus z, I'm associating with this and the derivative over x. Okay, then of course that derivative will also be there. Okay, so let's take it term by term. Okay, so let's start with this term, f of z. Okay. Maybe I should multiply it out. Okay, so maybe you all can help me. What was the first term that I had surviving there? If we just take the f of z term, right? So our integral f of z. Right? Is it okay? Okay, so what can I do with this term? I wanted to look carefully at this, this when I Taylor expanded f of x, the first order term is just f of z, right? And where did I have f of z? I had f of z at the bottom here, right? This is nice. Okay, so you can see both things. So I have this term. So this is just f of x times this probability, right? And there I have f of z times something, but I have to do something with these two terms because the other terms I had was df dx and d square f dx square. So that cannot, nothing can happen here. So this term has to somehow be dealt with that term on top. So keep this in mind. It's f multiplied by this t prime to t transition. Okay. Yes. Yeah. So the first term has that term, right? But this term has to combine, no, in some way. So that this term produced many things. It produced f of z into something, df dx, d square f dx square. And I have this minus f here. So I'm saying this term and the f that comes from here have to somehow combine together, cancel out, something has to happen. So now if you look at the form of this, it's f times the transition from t prime to t. Okay, just remember that. And now if we look here, we have f transition from t prime to t. The problem is this transition probability. Right? But notice what I have here. I have an integral over x. Yes, and whether this is less than epsilon or taken over the whole thing doesn't matter because anyway nothing contributes. So you can read this as the integral over x of the transition probability where I integrate over all x, and that is just 1. Okay. So this, because the integral of this is just 1 because I'm going from z at time t to some x. What is the probability of doing it for all x? That is 1 only. I have to step somewhere. Okay. So this is 1. So I can take this and this together, it becomes 1. So this integral will simplify. Right, dz. Okay, so this thing transforms to that because of the definition of the probability density, right? It has to integrate to 1. And now what is this? If you look at the previous term, they are the same. It's just a change of variable, right? So this thing will cancel with the second term. Okay, so we've knocked off, so we've gotten rid of that leftover term with the first term of my Taylor series. I have only 2 terms left now, the df dx and the d square f dx square term. Okay, and that is where we are going to use these things. So let us see what happens with the df dx term. Exactly the same thing will happen with this d square f dx square term. Okay, so what was the other integral now? I had integral yes? Please check and tell me if I'm okay. Right, so where I had f here, I have the second term of the expansion, df dx x minus z. This of course is a function of z only. Right, remember it comes from the Taylor series. So if you want, this is evaluated at z. So the only x dependence I have is sitting here. Okay, that's important. df dx is a function of z because I Taylor expanded about z, right? So the x dependence has gone in x minus z. This is only a function of z. So when I think about the integral over x, this is a function of z. It's like a constant. Right? So when I apply the integral over x, this is a constant. Right? This is some constant. It's only this that gets integrated. Correct? So I can split up the integral as d by dx of this stuff and all the rest. But what is d by dx of that? Again, of course, I have x minus z less than epsilon. Right? That is just a. So this thing becomes equal to so I don't do the z integral. So things that are functions of z are just sitting like as they are. I apply the x integral, right? And the x integral acts on x minus z and this transition probability. That's the first moment of the transition for small x minus z, and that is by definition A. Okay, plus order epsilon means those terms can be dropped. So now this is an integral over z. Now similarly, the other term, right, will give me the second derivative. I mean, exactly the same thing will happen, right? Instead of this, I'll have the second derivative. Here I'll have x minus z square into the transition probability, which will become b. Okay. So similarly, we will obtain, right, integral dz b times, but with a factor 2. This factor 2 came from the Taylor series, right? And then the same probability. Okay, now if you take this for the last term, which was x minus z the whole cube, right, that is like the third moment, which we have proven already is small. Right? It's epsilon times b. So that will drop off, and similarly all higher terms will drop. Okay, well, I realized I made a notational mistake, right? This, when I do the Taylor series, this of course is, it's a derivative with z. Right, so I know f as a function of z, the value at this small distance x is f of z plus a derivative with respect to z into the step. Silly mistake. Okay, so it's okay, right? So I'll have, in fact, I don't need all of this, it's just z. Okay, that's nice. Okay, so now what you see, we have reduced everything. The f term gets cancelled. You just have these two terms surviving, right? The higher moments also drop. So we now have an integral of a, some derivative of that function, right, times the probability. So let's bring everything together now. Now we don't need these things, we've used the definitions. So let's collect all terms. Okay, if we collect all terms and recall, yes. No, so if you think of a function of z, right, and I'm saying I'm at position z and I want to step to z plus delta. So you're saying I have a function f of x, correct? The function f of x is a polynomial in x, right, whose coefficients are not functions of x. So I mean, in that sense, whether you notationally write, it's the derivative evaluated at z only. That df ds z is a function of z.
It is a function.
Huh.
It is evaluated at z, but still, it should still be df dx. It is a derivative of x evaluated at z.
So if I say, I mean, in the end it doesn't matter, okay, but I'm trying to see how to convince you all. So if I say that I have a function f of x, okay, and I wanted to know at x plus x prime, and x, right? So let's say I have a function z, I want to find its value at z plus delta z, and z plus delta z is x. Then want to write it the way I've written. Right? So you think of x as delta z. So if I have a function f of z and I want to find it at f of x where x is z plus delta z, then I'll write f of z plus delta z is equal to f of z plus df dz delta z and so on. So the confusion is coming is because you are thinking of z as a point. Right? In the end, I can flip the variable, it's not going to matter. But so a cleaner way to think about it is, suppose if I wrote this, right? What would you do now? Right? You'll write df dz into delta z. And then now I just have to say z plus delta z is x. That's what I wrote. So it will be clearer if I want to be very pedantic, I would say, okay, I have a function f of z. I'm now choosing some z naught over which I want to expand. Okay, then I would say df dz at z naught. But x doesn't enter the picture because x is just z plus delta z. Okay, so for the recording, we were just trying to figure out whether this should be x or z, and so if you think of it this way, it's clear that it should be df dz. Anyway, thanks for the questions. It's nice to revisit these elementary things. Okay, so where were we? Yes. So now we want to collect everything, and let's recall the starting point, right? Where we were looking at the evolution of the expectation of f, okay, which I said could also be written as integral of f dp dt. Okay. So let's put that here, that RHS part. You notice I flipped x and z, right? But that doesn't matter, it's a change of variable. Because now I'm left with only z, no? So I've gone back to, okay, just to recall, right? If you go back here, okay, but this is a separate integral, right? I can change x to z, it's just a notation, just for convenience. So this is f of z ddt of the probability, right, where I go z and t prime, right, dz. So that's, I've just rewritten that there. Okay. And now this must be equal to what we have got here. So I have only two terms, right? I have A, everything is a function of z and t, right, times the probability of okay. All right, so if we take a step back and think about what we did, we started with wanting to find the expectation of this f, right, where the ddt was outside. And we said, okay, it's the same as this, let's keep it for later use, so we put it here now. But when the derivative is outside, we can apply the limit, right, and then that gave us a difference of two probabilities. And then to be able to do a Taylor series and to use the fact that delta t is small, we use Chapman-Kolmogorov to step from y to some intermediate z and then to the x. Okay. And then x minus z we could see was small. So that was a nice thing. We could limit the integral to small x minus z. And then we could do a Taylor series on f, y, so that we can introduce x minus z square, because that will allow us to use our definitions of the moments. So that's why the Taylor series on f was important. So we had f of x and f of z, and by expanding f of x around f of z, we could introduce x minus z and x minus z square. So those naturally gave us allowed us to put in our moments, first moment A, second moment B, and higher moments we know will go off. And when we collect everything together, we reach here. So what we have used is the definition of the limit, Chapman-Kolmogorov, to go from the far point y to a close point z, that is close to x, and then did a Taylor series treatment. Okay, and so we have got it. Now, if you look at these two sides, we want an equation for p. Okay, and if I compare it, see, the problem is that I have these derivatives on f instead of f. Right, so what I would want to do is get f out and put the derivative on p. Right, so what should I do? Is there some way I can make the derivative, let's just look at this term, right? Is there a way for me to bring the derivative onto p and bring f out? Yeah, so I integrated by parts, right? So let's try that. So integrate the first thing by parts. So remember, y and t prime are constant now because we're integrating over z, right? So this is only a function of z, this is a function of z, everything is a function of z. Okay, so do integration by parts. So I want to take, remember, first into integral of second. So I want to integrate out this, right? So this should be the second. A and p should be the, what I think of as first, right? So I'll have first into integral of second. This, some limits have to be applied here, right? And then I'll have a minus integral of, now partial derivative will come in, right? Because p is also a function of time. Okay. And can you do the same for the second term? Yeah. Sorry? So it's first into integral of second, right? And then minus integral, then I expanded that again, right? So again I'll get, just check if you get this. You have to do integration by parts 2 times, of course, right? So the first time you will get dp dz, then you do it again, you will get only p, second derivative, and then f. Correct. Put some percent. It's not there really. Okay, by 2. Okay. Okay, so now we have got somewhere, right? We have the f out, we have the derivatives on the p, right? We'll see what to do with that later, but at least there's some hope. But now you have these terms where we have to apply some limits. Okay, so because we're doing the problem in 1D, we've not specified at any time what is the limit, right? So what is the range of values that this x can take? Is it minus infinity to plus infinity or 0 to 1? That depends on the process, right? If I'm looking at stochastic process in some finite interval like in a box, then x will have some a to b range, whatever it is. But the point is, these will be some quantities, I have to just evaluate them at the boundaries, right? These are boundary terms. So what do I do with them now? Is there some way I can get rid of them? Right, f is arbitrary, so I can just choose some f which vanishes on the boundary. Okay, and then I drop all of these things. Right, so I drop this. Okay, why? Because I can always do that. So I've gotten rid of all my boundary terms, I just have these two integrals. So now what you see is, compare these two sides. I have the integral f of z is outside, those f's are also outside. So what I can do is bring all the integrals together and I'll have integral f of z. Okay, so I'll have integral f of z times some terms, right? Those terms will be dp dt plus this a d by dz of ap minus this thing, all multiplied by f. See? So now what can I do? Can I get a differential equation out of this for f, for p, sorry? Okay, so from here what I have now, right, there's a minus in front of the a, sorry. Right, so this has a minus, this has a plus, it will become plus minus, right? This is what I have. Okay, so but this looks like a differential equation, right? But only if I can say that this is 0. So can you tell me why right now I'm only saying the integral is 0? Why should this mean that this inside the brackets is itself 0? Right? So this is exactly the same idea that we used in our transport phenomena derivations, if you recall, right? That we will ultimately get something like this in things like Reynolds transport theorem and so on. And the idea is that, okay, this integrand could be positive or negative, but I can always choose f such that it is in some place where this is always positive, in which case for it to be 0, this must be 0 identically. Okay? Or it's again, like I said, right, this f of z is arbitrary. So you can make it a Dirac delta function. And the fact that this must always be 0 for any f must imply that this integrand itself is 0. Okay. So we have again used the fact I told you right in the beginning, right, that because f is arbitrary, writing this kind of integral form doesn't lose information, and now we can use that same fact. Because f is arbitrary, I can make it like a Dirac delta anywhere, right, and argue that this must itself be 0 at all points. Okay, so finally now I have let me write it like this. So I'll write it in the classic Fokker-Planck style. Okay, this is for P of x comma t given, sorry, z. Did I put x everywhere? Sorry, z. Given that I'm at y at t prime. Okay, that's what we have derived. Sorry, z. Yeah. Thank you. Okay, so f of z is arbitrary, so this must be 0, which gives me a differential equation. So this is the Fokker-Planck equation. Okay, so we'll stop here and say something more about this equation next class, including how to solve it, what kind of initial condition. Okay, we'll do that next time. But yes, so the most important thing to remember to look at right now immediately is it looks like an advection diffusion equation, the kind you would have for any concentration field, except the velocity, which is called the drift, right, and the diffusion term b, right, b by 2, right, that these terms, so it looks like it has a diffusion coefficient of b by 2, okay, if you want, I'll put the 2 inside. So b by 2 is like a diffusion coefficient, a is like a velocity, except that they are inside the derivative. Right? Normally when we do mass conservation, the a is outside and the b is inside only one of the derivatives. It will have d by dx of diffusion coefficient d by dx of c. So it is not the usual advection diffusion equation for a concentration species when the velocity and the diffusion are space dependent. If they are space independent, this pops out and it looks the same. Okay, so if you think back to our first class, when we said, okay, the probability PDF will evolve like advection diffusion, that's only for constant, like that is what's true in Brownian motion where diffusion is constant, then it is the same. Right? But otherwise it is not. If you do a mass conservation, assuming diffusion, you will get a different equation. Okay, so that's important. It's not, it looks same, but there is some subtlety. Okay, we'll say more about this in the next class. We've run out of time. So thank you everyone.